Good afternoon, and welcome once again to our Wednesday afternoon seminar series. This week, we're happy to have another guest speaker. Our speaker today is Professor Wenke Lee of North Carolina State University. Professor Lee received his PhD after studies at Columbia University in New York, and his area of specialization is in intrusion detection and other areas of information security. He's going to be talking to us today about some of his research work and development work in the area of intrusion detection. So please join me in welcoming Professor Lee.
Thank you, Smith. Okay. So here's the outline of my talk. I will first give a very brief introduction of what is intrusion detection, what it is supposed to do, and what's the problems we are having with this technology. And then I'll talk about a data mining process that can be used to build more effective intrusion detection systems. After that, I'm going to switch gear and talk about more recent research, which include the cost-effective modeling and analysis for intrusion detection, and talk about some information theoretic-based approach for anomaly, for building anomaly detection system. So why do we need intrusion detection techniques? Okay, so we have to look at it from the perspective of building a secure network. So how do you secure a network? You first have to analyze the vulnerabilities of your network environment, and obviously you want to prevent these vulnerabilities being exploited. Okay, but preventions don't always work. So you want to put out a second line of defense, meaning if the prevention fails, the intrusion actually comes in. You want to be able to detect that the intrusion has come in, and you want to respond to that intrusion. So intrusion detection sometimes still fail. For example, denial of service. There's no way to prevent that. And by the time that you detect a denial of service is happening, normally it's too late. So you really have to have another line of defense, meaning how do you tolerate intrusion? So how do you build intrusion tolerant systems? But this talk, we're going to focus on intrusion detection techniques. So for intrusion detection to work, the assumption is that system activities can be observable. You know, when you log into a system, if you turn on the audit mechanisms, and by looking at the audit data, we can find out what you have been doing on the system. So we have to assume that. And this is a pretty much a very good assumption given the audit mechanisms that we have nowadays on network and on operating systems. And another assumption is that the normal and intrusive activities, they must have distinct evidence in the audit data. I think about intrusion detection as similar to like investigating a crime. If you go to a crime scene and you cannot find any evidence, then there's no way for you to solve that case, right? So same thing here, that we have to assume that the normal and intrusive activities, they leave distinct evidence. So really, intrusion detection, the goal is to analyze the audit data and find out the evidence of intrusion. So the main techniques are misuse detection, which is based on patterns of known attack programs. So the idea here is that if you knew that a attack is coming from a widely published program, for example, you can download such attack programs on the web, and you can study these attack programs and basically abstract the patterns of actions of this attack. Then you can build a pattern matching engine to monitor the system activities, so that next time when a high school kid downloaded this program and run it again, you know, its action is going to match with your pattern, and you can detect this particular known intrusion. So that's misuse detection technique. Another different technique is called anomaly detection here, And the idea is that you don't assume you know the attack method to begin with. So all you know is the normal behavior. So the idea is that you want to build a set of normal profiles that characterize what's normal. Okay. Then you observe runtime system activities, and if that measure deviate from your normal profile significantly, then you can draw a conclusion that, hey, something must be wrong. Let's investigate. Maybe that's an intrusion. Really, you need both anomaly detection technique and misuse detection techniques. Now, what's the state of the current intrusion detection techniques? The assessment is that it's not as effective as what we hoped they are. The true positive rate, meaning the percentage of intrusions that can be correctly detected, are kind of low. For example, a lot of signatures, meaning the patterns of known intrusions, they don't work very well after they are developed for a particular environment. So if you develop a set of intrusion patterns for a particular network, and then you move these patterns and install on a different network environment, they may not work even if the same attack program is run on that same network. Why? Because different networks may have different configurations, different traffic patterns, and those signatures depends on not only the attack program but also the background network configuration. So if the background configuration change, the attack signature may not work. So another problem is that there are very high false positive rate. High positive is basically a situation where a normal activity is being considered as intrusion, which is false, right? And this is especially a problem with anomaly detection mechanisms, because for anomaly detection mechanism to work, the idea is that you assume what's normal and you detect what's deviating from normal profile as possible intrusions. But what's deviating from the normal profile could just be the new normal behavior that you have not observed previously. So when you characterize a normal behavior as possible intrusion, you result in a false positive. So why intrusion detection techniques are not as effective as they should be, or as we hope for? Really, I can think of the reasons being we don't have very good theoretical foundations of what is intrusion, how intrusion detection should work. And also, because of that, we don't have very good development process to develop intrusion detection systems. So most of the systems are developed using what I call pure knowledge engineering techniques. Basically, the process involves studying a particular network configuration, network operating system environments, the application software, and the possible attack methods that can be launched. So based on that knowledge, you basically you hand code the patterns and install them and hope that they will work. But the network environment is really too complicated. So just going through the knowledge engineering process is very slow and very expensive process. So part of my research is that we try to build some tools that can be used very widely, so that you don't always have to go very specific piece of knowledge and encode them. The idea is that you can just get the audit data from a system, and then you apply this set of rules, this set of tools that would give you some starting points. Okay, these starting points are, for example, statistical patterns of the audit from the audit data that tells you what's the normal background traffic of your network, when intrusion is launched in your network, what's the unique patterns resulting from the intrusion. So from those patterns computed from this set of tools, the engineers can quickly come up with better intrusion detection rules. Okay, instead of going pure manually from the beginning. So that's the main motivation. The approach is basically three main steps. The first step is that you want to compute statistical patterns of the system activity from the audit data. And then you want to identify what are the intrusion patterns. Okay, what are so unique about this intrusion that's different from the normal? Okay, and then based on that analysis, you construct a number of features that can uniquely identify intrusion, meaning separate intrusion from normal. Okay, so based on those features, you can easily come up with intrusion detection signatures or rules. And we have gone through some development in the past few years and has been evaluated on one of the government-sponsored evaluation, and we have done quite well. So, so the method has been validated to a degree. So the process of applying data mining techniques to build intrusion detection models is the following. So we start with raw audit data, right? And that's what you get from the system. And then, since it's binary, we have to process it and convert it into ASCII data and analyze the packets and events from the audit data. And then we again summarize the packets into connection data, or summarize the event into a session. So a session is, for example, a telnet session. A connection can be like FTP connection. So each of these connections are defined according to a schema that consists of a number of features that will be very useful to separate normal connections from intrusion ones. Okay, so how do we define those features? Well, we first compute the patterns from the connection records, and then based on the unique intrusion patterns, we add features that can separate intrusion from normal ones. So once we have those features, then we can build very predictive models to say, given a connection record, I can tell you whether this is intrusion or normal. So that's the whole process. So obviously, this process can be iterative, meaning sometimes you find out that the performance of the model is not as good as you hope, and you can go back to define more features. Okay, and how do you do that? Well, you have to go back and compute more patterns. So this process is iterative. So just give an example of what I mean by processing the audit data into connection record. So we begin with TCP dump packet data, right? And then we summarize we process the packet level data. So each line of the first box is basically one packet, right? From source A to destination B, for example. And then, a network connection has many packets, right? So we analyze the packet level data and then summarize what's going on within a connection by looking at all the packets belonging to that connection, and then define a number of features for each connection. So each line in the second table is basically a connection record. So you see a number of features. For example, the timestamp, the duration of the connection, the source and destination, a number of bytes being transferred from source to destination, and what's the service on the destination for the connection, and a flag. A flag here is a summary of the connection behavior according to the protocol specification. For example, a flag SF is for TCP, meaning it has been seen and finned according to the specification. And REJ meaning it's basically simply rejected by the destination, and so on and so forth. Now I want to briefly talk about what are the data mining algorithms that would be useful to build intrusion detection models. So there are many algorithms in data mining field, but there are only a handful that I think are relevant to intrusion detection systems. The first one is what I call what we call classification algorithms. So in classification, the task is to map data items into predefined categories. For example, you want to classify apple and orange. Given set of apple, orange, you want to separate them, right? So I think intrusion detection can be naturally cast as a classification problem, because given a set of connection, for example, whole day's connection, you want to classify, hey, is this connection normal, or is this connection a intrusion? So it's a natural fit to this classification paradigm. And we use rule learner here to learn classification rules, okay? And why we use rule instead of more complicated paradigm like neural nets? Well, the idea here is that rules are very intuitive for human engineers to interpret and to process. So the idea here is that we don't want our tools to replace the IDS developers. I mean, these tools should be like a development toolkit. So the outputs of this toolkit will be understandable to the human. So we stick with the rule format. Another algorithm that would be useful is what we call link analysis. So link analysis can determine the frequent relations between system features. And this will turn out to be very useful, and I'll give an example. Another kind of algorithm is called sequence analysis. And we know that in system and network activities, most of the actions, they have some kind of temporal context. For example, for denial service to work, at least some of the denial service that relies on flooding the targets, they have very, very strong temporal statistical pattern. For example, for it to work, you will see a lot of packets coming to the victim in a very short period of time. So that kind of sequential information is very useful for intrusion detection purposes. So let's talk about classification rules. So a rule learner is basically given a set of data where each record is defined using a set of features. The rule learner is trying to pick up a set of conditional tests that basically use the most distinguishing and concise feature value test so that it can separate data into different categories. So for example, some rule set here that we actually build, the first rule says that if the connection has more than one wrong fragment, meaning the fragmentation is not done according to the specification, meaning, for example, the offset is overlapping, it's not multiple of 8 bytes, something like that. And also, the protocol is ICMP. Then it's a non-intrusion called ping of death. Okay, the idea of ping of death, you send fragmented ping packets that the offset is wrong, so it would crash some systems. So that's a rule that can be learned. And also the second rule is that to detect Smurf attacks basically a lot of ICMP echo request is being sent to a broadcast network. So you will see a lot of a victim host getting a lot of ICMP echo request. Okay, so that's an example of the rule here. And for the classification rule to work properly, the condition, I mean, the key really is the conditional test for the feature values, right? So if the connection records don't include the features that can distinguish normal and intrusion records, your rule is not going to be very effective. So really the key here is to find out the features that its values can distinguish normal and intrusion. So in the information theory term, those are the features that have very high information gain. Okay, high information gain is the same as what's called reduction in entropy. And entropy is basically a measure of how pure the data is, or how impure the data is. So just give you an example. If you give a data that has only one class, meaning it gives me a basket of apples, then entropy is 0. Why? Because anything that you pick up from a basket, I know it's apple. So I don't have to use any, there's no uncertainty here. But if you have more than one kind of fruits, then I have to use several bits to represent whether this is apple or orange or something else, right? So entropy really measures the impurity of the data. So if you have a feature that have high information gain, that means it can separate data into more pure subsets, so that each subset is in its own category, which means you can separate data into intrusion or normal. So how do you find those features? So our idea is that you first compute the patterns, statistical patterns from the audit data, and then you compare compare the patterns of normal and intrusion. Then you identify the intrusion-only patterns, and then use those patterns to define the features. So what are those patterns? And the first one is what is called association rules. Association rule basically categorize the correlation between system features. So as an example here is that suppose you have an audit data that consists of the shell commands that user type, right? So each command is one record that has the command name, the timestamp, the host. So an example here is that you will see when the user sends email is from the host A and in the morning, okay? 30% of the time, so that's a confidence. And this activity accounts for 10% of its daily activity on the host. So that's kind of a statistical measure that would be useful. Another example here is called frequent episode. It's a sequential kind of pattern. So go back to the shell command example. This example says that after the user VI the C program, it's going to compile the C program within 5 command time window. So this kind of temporal patterns would also be very useful. So I'm going to skip some of the details here, but the main idea of computing these patterns is the following. So suppose we have intrusion data, we compute the patterns, and then we also compute the patterns from a set of historical normal data and attack data that we store in the archive. Right? And then we compare the patterns that we compute from these two sets. And then we identify what's unique about this set that we want to study for this intrusion. And then based on the identified intrusion patterns, we define new features. And we add those new features to the training data so that each record now is being expanded to accommodate the new features. And based on that, we can apply some learning algorithms to learn the models. I'm going to give an example here. So, for example, go to here. So this example is a SYN flood pattern. So SYN flood pattern is the following: that the attacker will going to send SYN request to the victim, but never finish the handshake. So the victim is forced to hold the request in memory, and sooner or later it's going to run out of buffer space, and the new connection cannot be served. So it's kind of denial of service intrusion here. So this pattern says that all these activity are to the same host. Okay, and for each of these activity, they're to the same service, HTTP, meaning here the target is HTTP. And the flag is S0, meaning only one SYN packet is sent. There's no follow-up for the handshake. So once this unique intrusion pattern for SYN flood is identified, we can add the following features. Since all these are to the same host, then we're going to add a feature, say we want to count how many connections are to the same host. Okay, in the past 2 seconds. Why 2 seconds? Because that's the time window that we compute from the pattern, for the pattern. And then for all these connections to the same host, we want to also compute the percentage of connections that are to the same service. Why do we do that? Because the same service is being used in the pattern. And also the percentage of connections that had a S0 flag. Okay, so based on this pattern, we can add 3 new features. And we can prove that because of adding these new features, now the intrusion records will be very different from the normal ones, because the values of these features for the intrusion ones are very different from the normal ones. So in other words, these features have very high information gain, and they can be used in the classification rule algorithm to learn a very accurate classifier. So I'm probably not going to go into detail of the evaluation, but just give you one example here. That we analyze a huge amount of DARPA data. That the MIT Lincoln Lab collected from a simulated network environment for Air Force land, and they have embedded intrusions in their training data. So they will tell us what are the intrusions, where in the data. So based on this training data set, we computed patterns from the intrusion data, and then we constructed new features to characterize what's the traffic model for this environment. So some of the features are the following. For example, how many connections are to the same host, and percentage of rejected connections, percentage with SYN errors, percentage of different services, so on and so forth. And these features are basically automated. They are generated automatically from the patterns. And the result seems to be very good. We have a very good result from the evaluation. So there are some limitation on this framework. First of all, it's still a misuse detection mechanism, meaning you really need example of no intrusion in the training data for the data mining algorithm to work here, because we are learning classifiers. So for the classifier to work, you have to give example of each category. So you have to give example of what's normal, you have to give example of what's intrusion, and you hope the classifier can automatically learn a rule to distinguish normal and intrusion. So initially we were very naive, and we thought that, okay, so what, you just download attack programs, run in your network, obtain your customized attack data, apply our tool, then you can learn the customized detection rules that will work well in your network environment. But guess what? Not many people want to simulate intrusion in their network, because their network is used for production, right? So that's a major limitation here, and we really don't know how to solve it yet. Another limitation is that we assume a fixed session definition, mainly because it's an offline system, meaning the detection rule would work after the connection has terminated, because all the connections are defined using a set of features, and if those features are not populated yet, there's no way for the rule to work. But for the features to be populated, the connection has to be terminated first. So it's not a real-time system yet. Although we are working on some method to basically transform the offline models into real-time versions, but that requires a lot of engineering work. So I'm going to talk about some recent research. I'm probably going to skip this part. Go to the anomaly detection work. I think this is very important, because if you think about misuse detection techniques, the major limitation there is that if some attacker is going to invent a novel, meaning completely new intrusion, the misuse IDS will not work. Why? Because it's based on signatures of known attacks. So if someone invent a new method, completely new, it won't have a signature in your signature base. So it's going to probably go by without being caught. So really, how do we detect novel intrusions? The only hope, I think, relies on anomaly detection method. Why? Because it doesn't assume knowledge of intrusion. It basically tries to learn, okay, what's normal, and then detect what's deviating from normal as possible intrusions. Now there's a lot of problems with the current anomaly detection techniques. Actually, I don't know any commercial IDS use this technique, because it's not working right yet. Okay, it's a lot of very high false positive rate, but again, like I said, I think it's the only hope to detect novel attacks. So I try to study that. So our main focus is on how do we, given a set of audit data, how do we determine what's the best model that we can build? Okay, and how do you predict the performance of the model once you build it? To say, okay, if you move it to some other environment, what do you expect? What do you expect its performance will be? And our approach is, again, based on some information theoretic measures that we can compute from the audit data. So we start with a very simple case study. It's anomaly detection for Unix processes. So, for example, sendmail is an example of what's called privileged Unix process, because when sendmail runs, it runs as a root, right? And sendmail is a very complicated piece of software. It has a lot of bugs and holes. So it's a target of constant exploits by the hackers community. Right? There's a lot of buffer overflow exploits on sendmail that, because sendmail runs as a root, if you buffer overflow sendmail, you're going to able to attain a root shell, which is not a good thing. So how do we build an anomaly detection system for sendmail? So the University of New Mexico group a couple years ago had come up with a very neat idea. The idea is very similar to the immune system of human body. It's like human body doesn't have prior knowledge of all the diseases that it's going to get in. All the human body has is about itself healthy state. So if some viruses, unknown viruses come in, the human immune system is going to respond and try to attack the virus. It doesn't have to have prior knowledge of that virus, right? So similar idea here is that if the Unix process can have an idea of what's its normal profile, normal runtime profile, then it can probably detect exploits. So the idea here is that if you analyze the system calls that are generated by sendmail in the runtime, and so you have a trace of system calls, consecutive system calls that are made by sendmail process. And if you take a sequence of sliding window of the sendmail trace, and then you take each of these sequences and put into a database, then you pretty much we have a database of unique sequences of sendmail. If you run sendmail many times, you're going to collect a stable set of system call sequences. So the idea is that once you have that stable database, then you can observe a sendmail run, and then compare the sequence there. And if you see a lot of system call sequences that don't match with your normal database, then you can probably conclude that, okay, maybe sendmail has been exploited to run something else. Now our approach to this problem is that, okay, again, let's cast it to a classification problem, and we say, okay, the idea is that given the first k system calls, can we determine what's the next one, k plus one? I mean, this is not new. I mean, it has been done previously by various groups, including when I was at Columbia. But there's one problem that people kind of constantly ask us, and no one was able to answer. It was like, okay, how do you determine the sequence length? How do you determine k? So the University of New Mexico people, they come up with the sequence length 6, and when asked why do they pick up 6, they say, oh, we try different numbers and this happened to work. So, and we don't like that, and we say, okay, do we have some kind of a systematic approach to understand that? So, first I'll give you some background. So, here is a plot of different sendmail traces. They're all normal traces, and if you plot the misclassification rate, meaning the errors that they made when predicting the k plus 1 system call versus the system call length, you see that as the system call length increase, the error rate also goes down. Okay, that's nice to know. So you can say, okay, why don't you just build different models using different system, using different sequence length, and then pick the best one. Well, building such a model takes a lot of time. So if you have to exhaustively build all the models, that's not very practical. So so the idea is that do we have like simpler method that can determine what's the right sequence length? So another plot is that the idea that the short sequence system calls would work is that if you look at the normal profile, the misclassification rate is kind of low, like below 10%. But for the intrusion trace, they are normally above 15%. So really, this proves that using system call sequences, you can distinguish normal and intrusion traces. But like I said, the problem is how to determine the sequence length. So our idea is that we measure the entropy of the data. So first of all, what is the entropy? Like I said previously, entropy is basically a measure of uncertainty of the data set that you have. So if you have a data set that has only one class, meaning all apples, there's no uncertainty. Uncertainty is 0. Okay, so if an entropy value is very small, that means the data is very pure, it's very certain. So we also compute conditional entropy, meaning if I give you X, how uncertain is Y? Okay, you don't have to worry about the formula here. So how do we calculate the conditional entropy for system call data? The idea is that given a system call sequence, for example, A1 to AK, how do we predict the next one, AK plus 1? So we can say, okay, now the Y is the K plus 1 sequence, X is the K sequence. So by computing the conditional entropy, meaning given the first K plus 1 system calls, what's the, how much uncertain it is for us to determine the K plus 1. So we can compute the conditional entropy. Some detail here, but basically, we can see that for all the system call sequence that we have for the normal trace, that's a plot of conditional entropy versus the sequence length. And again, you see that the conditional entropy drops as the sequence length increase. Okay, and for the SAML daemon, the previous slide was the SAML clients. So the daemon also exhibit similar behavior in terms of the conditional entropy versus the sequence length. Now, why am I showing you this? Well, now if we normalize the conditional entropy between 1 and 2, and again the misclassification rate between that same value range, you see that the two plot almost match exactly. Okay, and this is computed using all the traces of SAML, combine them into one trace. But if you want to compute the mean of all traces, basically you see the same behavior. Again, meaning the misclassification rate and the conditional entropy, they kind of match. The plot match together. So this tells you that you can compute conditional entropy of the system called trace, and then you can pretty much determine the range of the performance of the model that you can build. But by just looking at the conditional entropy, you can determine, okay, do I want to pick 6 or 7? Well, there's not much gain in terms of the conditional entropy there. So pretty much they stay the same. But if you pick system call length, let's say 2, obviously that's not very good because the conditional entropy is very high, meaning there's a lot of uncertainty there. And also, you can see the trend that as you increase the length, the sequence length, the conditional entropy drops, and so is the misclassification rate. Okay. So the question is, what is the best sequence length? Do we use as long a sequence length as possible? Well, from a pure accuracy point of view, probably yes. But if you talk about some efficiency in runtime, meaning how fast can you determine and catch the intrusion, you probably don't want to use a very long sequence length, right? So it's really a cost-effective kind of consideration that you have to think about. So basically the idea is that how do we get the biggest gain while paying the least cost? Okay, so what's the cost? Here we define the cost to be the time that is required to process one system call sequence. Okay, and then we define the gain to be the accuracy of determining whether the sequence is intrusion or not. So really, what's the accuracy? Well, simple. The accuracy is just 1 minus the misclassification rate, because misclassification rate is basically the error rate. So 1 minus the error rate is the accuracy rate. So if you plot, so here's the time to process one sequence, the time versus the sequence length, and you can see pretty much it's a sublinear cost. Okay, versus the length of the sequence. So if we plot a graph of accuracy divided by time, here's what you get. Basically, that's a unit cost gain plot. So here the idea is that we want to see what's the trade-off between the accuracy and the time. Okay, we don't want to just consider the accuracy. Okay, and you can kind of see that, well, initially you have some big gain, and then kind of taper off after a certain length. So this gives you some kind of mechanism to determine, maybe what's the best sequence length. Okay, by considering both the accuracy and the time or cost. Okay, and obviously if you have different cost function, the plot may not look the same. But that's the idea, that you want to consider not only the accuracy but also the cost. Okay, so the conclusion is that I think data mining techniques can be used to help us build better intrusion detection systems. Okay, not only just the tools that we use, but also the mathematical foundations underlining these tools. For example, the information theory, the statistical and probability theories, and I think they have some values in this domain. And there's some future work that I want to mention. My assessment is that right now the research IDS or the commercial IDS become very good in terms of catching attack actions, single attack actions. For example, we can very accurately identify, okay, this connection is an intrusion, especially if it's a known one. But what we really need to develop is what's called correlation techniques to understand attack scenario. So suppose you detect an intrusion. Well, then do we know what's the intention of this particular action, or where it comes from? Is it because of someone else had planted a backdoor previously? So how do you piece all those information together and understand an attack scenario? That's going to be a major research topic. And I think the idea, I think one of the approach would be you plan multiple sensors in your system. For example, the agent system that we developed here at Purdue. But then the idea here is that you want to, how do you combine the evidence or alarms from the multiple agents and then correlate and give a clear understanding of what's the attack scenario, not just individual attack action on single network elements, but an attack scenario target to your whole network. I think that's a very important work. Also, we're trying to apply very similar approaches using data mining techniques to build intrusion detection systems for emerging environments. For example, a wireless ad hoc network. There we want to study, for example, how the ad hoc routing protocols can be categorized in terms of normal routing behavior, so that if some enemy, some malicious user steals the handheld unit and starts to broadcast false routing information, can we detect that kind of intrusion to a wireless network? The wireless network environment is very different from the wired network environment and gives a lot of challenge. For example, in a wireless network environment, the physical layer is wide open, right? So the attackers can actually attack that layer also. In a wired network that we run here, no one can attack your Ethernet network without going through your firewall first, right? And also in a wireless network, especially the ad hoc network, the topology is very dynamic. There's no fixed routers, so you cannot really just place a intrusion detection. You cannot just play an IDS in a fixed point in your network and expect that to be able to monitor the whole network. In a wireless network, every single node can be an entry point to the network environment. So you really have to place your IDS on every single node. And then it comes again to the problem of how do we correlate, how do we communicate and cooperate, determine what's the state of the network. Because now your IDS functions really distributed to all the nodes. Then how do you reach a centralized determination? So that's going to be also a very challenging topic. So that's pretty much what I want to cover today. Yeah.
I have a question on the data mining aspect.
Right.
One of the benefits claimed for data mining is that with enough data you can identify features and groups of features that indicate conditions you're interested in,
right,
that an expert might not otherwise be able to spot.
Right.
So I'm curious, in your experiments, did you identify any features that were surprising to a domain expert as being indicative of an intrusion? And did you come up with any patterns of features that indicated attacks that, again, were significantly different or surprising compared to the standard misuse patterns that you might find?
Okay, that's a very good question. Actually, when I presented my thesis, one of the committee members said, well, all your rules are very straightforward. I could come up with those rules too. So my answer was that, well, that means my system actually works, because if it comes up with some rules that you cannot understand or completely outrageous, that probably means that my system doesn't work, right? But in terms of whether the system produces surprisingly good features, I think the answer probably is yes, but may not be a fair answer, because I only compare my system with only a handful of systems, for example, Emerald, right? And I look at their features, they seem to be very, very simple-minded. And it so happened that the feature that I computed seems to be more general. For example, if I go back to here fast enough, right, so you can argue that all these features are kind of general, not specific to one attack. So I think that's the one of the advantage for data mining, is that because the tool itself runs automatically, you can basically cram a lot of attacks in a huge data set, and the data mining algorithm is going to compute what's the most generic features that can distinguish normal from intrusions, versus a human tend to say, okay, for this attack, I know this specific feature is going to catch that, and for this other attack, I know this specific feature is going to catch that. But for data mining, maybe we can generate a more abstract and general features that cover both. So I kind of see some evidence, but although you can argue that a human expert can come up with the same set of features, it just so happened that the comparison may not be complete yet.
Let me just make the observation that if you were to run this against network traffic collected that was encrypted, a VPN observing from the outside, or looking at ATM traffic, maybe lane on ATM, where you can't apply the normal misuse rules because you can't really see into the data. You don't have visibility. If you can still find patterns, then you've got something very interesting. Right.
Actually, I tried that before I go into the packet portion, I mean the data portion of the packet. I was trying to find out, okay, for example, I want to detect the guest password thing. And you will see that because the password prompt is being prompted several times, you actually will see a pattern of number of bytes being repeated at the beginning of the telnet connections. So that kind of pattern supposedly we can compute. But I just basically jump into my knowledge engineering instinct immediately. So okay, well, why don't I just analyze the data portion? So I have to be perfectly honest that I started as mainly a data mining guy, but now I'm more like a security guy. So I cannot objectively say that I don't include any knowledge engineer part in my system. It's kind of mixed. So my stand has changed substantially between the time that I proposed my thesis to now. Right now, my stand is that I don't think data mining will be a black magic that can replace a lot of knowledge engineering work. But on the other hand, it's going to provide a lot of help. for example, computing the patterns, using the information theoretic, the entropy measures to guide you through the development process, and that's what I think the value will be. And it will never be to a point where it can replace the human experts, because right now I'm a human expert already. Yeah.
I get the impression that most of your work has been based on using network data.
Actually, I tried on BSM data too. That's included in my thesis, but I never presented that research because initially I thought by having one model that monitors TCP dump and one model that monitors BSM dump, I'm going to gain a lot. But it turns out that because the way that compute features, because the way that the evidence would come up on both sources in a similar fashion. So although the feature definition is not the same, but they're actually capturing the same evidence. So I'm not gaining anything.
So do you have any comments on that data mining techniques performing better on network data or BSM data, or any observation at all, like what you're...
Right, so what I showed, the evaluation result was based on BSM, was based on TCP dump data. I did not have time to do the BSM when the evaluation happened. But afterwards I did that and actually performed very, very well. Actually, one of the advantage for this tool is that I don't have to be audit data source specific. The same tools would work for BSM as long as it's processed into a session format that has a number of features. And it will just go there and compute the patterns and add more features, apply the rules, and then learn the rules. So all you need to do is do the hard part, really the knowledge engineering part, meaning how do you process the TCP dump data or BSM data into session or connection record. And after that, it's quite easy and automatic. Yeah.
Question about the anomaly detection system.
Right.
When you said that it was analogous to the New Mexico stuff, analogous to the human immune system in that.
Right.
Well, the question becomes, what happens when the system state changes? It's kind of like an organ transplant in a human, and we know how poorly humans react to that in terms of their immune system. So how would a system like that deal with an organ transplant, like a libc change or something?
Right. So in that case, then you have to collect the data and retrain. I mean, that is true for all data mining based approach. And actually, what I didn't mention was that the reason that I stick with the entropy or information theory based measure was that I'm hoping to prove that I can, based on entropy measure, I can show that, okay, the environment has changed. So this model will not work anymore. We have to collect the data and retrain. Right now, we just don't have a mechanism to predict and observe that change. But I guess, I'm hoping that in 6 months to a year, I can develop some tools that can tell you, okay, now because the entropy measure has changed, the environment has changed, the model will not work anymore. We have to retrain. Yeah.
One more question. When you're talking about the length of time, like the trace time,
right?
When you say that you were optimizing it for efficiency,
right?
And you were talking about the cost of analyzing a trace,
right? Was
the cost compute time or was it latency in detection?
Actually, well, it's basically the same to me. It's like feeding a system call sequence. How much time it takes in terms of milliseconds before it reaches a conclusion, yes or no. So you can think of that as latency time or computation time. I think they're the same.
Well, if it's compute time, then the question becomes, why can't you feed the data off to another box that doesn't have a compute time overhead problem?
Well, okay. Really, for whole space, for catching process anomaly, you want to do it there on a kernel, I think. By sending the system call data over to another box and compute, to me, it doesn't make sense. Yeah.
Well, just a comment on that is that in most audit data, traces don't always appear until after the operation completes,
right.
And then you've got to reorder them. So there is some extra cost involved.
Right. So I heard that for BSM, there's a built-in 10 millisecond delay between the completion of the action to the time that it shows up on your audit data. So there's already some latency built in there already. So I didn't want to go into that because it's so much system and architecture, is still there. And right.
So was I correct in understanding that you were indicating that the findings for things like the window length and the system called prediction, that was not generalizable, that if I were to say create a new daemon, I'd have to figure out how to break into it in order to train a system like this?
Right, so basically I don't think you could have a formula, say, or plug in some parameters of SAML and boom, I'm going to compute a length for you. I don't think that would work. Why? Because, I mean, all these programs, they are like handcrafted to begin with. I mean, they're not following any formula or anything. So the best you can do is you gather the audit data, and then you compute with confidence, with certain confidence that what's the best sequence length. So if you want to train a model for different program, you have to go through the same exercise.
But do I have to figure out ways to break into the system to compromise it or exploit a vulnerability in it in order to build the data that you're using?
I don't quite understand the question. So
for the Sentinel,
right.
The University of Mexico thing,
right.
They run a normal operation, they run a series of attacks against it, so that way you have good behavior and attack behavior.
Right.
Let's say we create a new mailer program to replace SendMail.
Right.
Do I have to figure out how to break into that system in order to get data that says this is good behavior, this is someone breaking into it?
Oh, actually no. The data that we use to plot the conditional entropy, we use pure normal data. We don't use any intrusion data. I mean, I only show you one plot to basically show you the idea that this works because if you happen to have intrusion traces, the error rate is much higher than the normal traces. So that's the evidence that this kind of profiling will work because it distinguishes a normal trace with the intrusion ones. But in the training, to get conditional entropy and the error rate, we don't use any intrusion traces. We use only pure normal traces.
Yeah. A complement to Jane's question about types of intrusions, whether you found something new which was not known before.
Right.
But were there types of intrusions which are known which you were unable to pick up? Was there a pattern in those days?
Right. We have some. Yeah, there's some known intrusion that we don't pick up because, okay, that's a caveat of data mining approaches. Data mining approaches are based on pure statistics. So they will say, okay, let's say you give the data mining program, let's say 1,000 examples and only one intrusion. The data mining program may ignore that example. Intrusion example because statistically it's not important. It's only 0.1%. So some of the rules that it built already have error rate. They are saying that, well, this rule will work 90% of the time. Which means there will be 10% of the time we will miss that intrusion.
In intrusion detection, you really are not looking for evidence. You're looking more for the anomalies and the outliers. And if you can identify what is normal, you look for what is abnormal.
Right. So what I'm saying is that it's very difficult for the data mining program to compute a rule that's 100% accurate because of some conflicts of the feature that they select. So it has to basically select a set of features that agree with the majority of that intrusion classes. So you would miss some of the instances of the intrusion class. I mean, one way that you can sort of somehow alleviate this problem is that you can put some weight on different intrusion classes. For example, you say, okay, buffer overflow, I want you to be 100% accurate. And then you can force the data mining algorithm to learn very specific rules, very similar to a human hand coding style. But for some other intrusion, you say, okay, I don't want you to spend so much time. You can be less accurate, and then it would be more. It would be faster to compute the rules. So you can sort of alleviate that problem. Right. So. I don't know whether I answered the question right.
Were there types of attacks, of known attacks, for which you were unable to compute reasonable features?
Yeah, for example, guess password. So how do you know? Okay, so is it failing to log in 3 times indicator or 5 times? So some people choose 3 times, then it might have some false alarm because you happen to be stumbling. You maybe you didn't drink enough coffee, so you keep having wrong passwords. But if you raise this, okay, five, you have to fail in 5 times, then you're going to miss a lot of intrusions. So how do you set that threshold? So just like I said, the data mining algorithm is going to pick this threshold. They will agree with majority of that, but then it's going to miss some of the attack. So, but I guess that goes with the hand coding too.
That's why a lot of the systems that have been done along these lines, like CMDS and the work at University of New Mexico and others, combine the two.
Right.
To make it work.
Right.
Any other questions? Well, thank you very much.